All right, so on Friday, we learned how to plot points in the polar plane. Up until now, what you guys have been using, the XY axis, those are rectangular coordinates, or what's called the Cartesian plane. On Friday, we talked about how to plot points in the polar plane. And when we have a point in the polar plane, it's r first, theta second. What does the r stand for? Radius. And theta is what?
Angle.
Yes, this is our angle in standard position. And we learned how to do some very basic graphs. If we had an equation that was just r equals some number, what shape did it make for us?
Circle.
Circle. What about if I had just theta equals some value?
Line.
This was a line. The circles that we looked at when it was r equals a number, where was the center of that circle? Yeah, the center was the origin. We're going to start talking about some special types of polar graphs. You'll notice circles show up again, but these are not just r equals and then a value. This is r equals a cosine theta or r equals a sine theta. These are circles, but where the center is not at the origin. So if you will look at that single sheet of paper that's just one-sided that has all those different pictures of the graphs on it, if you look up at the top, it has the different circles that have this form. I'll bring this right back up, but I want to put this up on the screen for right now. So there's four possible ways our circles could come out. They could come out to the left of the origin or to the right, above or below. What kinds of equations are going to result in our circle being either to the left or to the right of the origin? Positive or negative what? Look at the equation. It has the equation down here. What do you notice is similar about these? It's cosine theta. If it's positive cosine theta, it's going to be to the right of the origin. If it's a negative cosine theta, it's going to be a circle but to the left of the origin. What about the ones that end up above and below? Those are the sine thetas. So when A is positive and we have a sine theta, the circle is going to be above the origin. When A is negative, but it's a sine theta, circle is going to be below the origin. So far, so good?
Yeah.
The period on all of our circles that have this form is going to be pi. We are going to be using a table of values to graph these. And so knowing what the period is going to be really important because that tells me how far out I need to make my table. Because once we've gone around our unit circle from 0 to pi, if we keep going around the unit circle, those values are just going to repeat. I'm just going to end up tracing the same circle over and over and over. So I only need to take my table as far as pi. for any of our circles. All right, and then this is the next one we're going to talk about. This is pronounced and I'm going to kind of butcher it. It's a French word. It's limousin. I said it right? Woohoo!
No, I don't know.
Limousin. I do know that the C with that little, like it almost looks like the end of a 5 on the end of it down below, that makes that C make an S sound.
Sound right to me.
Does anybody have any idea what this means in French?
Almost circle.
It means snail. It means snail in French. And if you go and look at that paper that has all the different graphs on it, you can kind of see why.
Anything can look like a snail if you try hard enough.
Yeah, like you got to try pretty hard, but over here it kind of has a flat bottom, and then it's rounded up on top, so you can almost imagine this snail moving along the ground. There are 4 types of limousins. Some of our limousins end up with this inner loop on them. Then we have this guy right here, cardioid. Does anybody want to guess at the root word for cardioid?
Cardio.
Cardio, close. Cardio means what?
Heart.
Heart. This, if you look at it, it's kind of hard to see in this picture. It comes together right here. It's more rounded on the end, but up at the right here near the origin, it comes in like a classic heart shape does. Like both sides are going to fold in and make a point right there. And then we have a dimpled limousin and a convex limousin. You guys do not have to memorize all of these, but I want you to be exposed to all of these and that they do have slightly different names. All right? But these are 4 different types of limousins. Important things to know about our limousin. These have a period of 2 pi. Talk to me about similarities and differences in the equations between circles and limousins. Similarities and differences. What do you notice about the way the equations are between the circles and the limousins?
The Limousines have they have a plus and then it's B times instead of A times.
So these, our equations are going to have a plus or a minus in them. And then it's also going to have a sine or cosine. Our circles, you don't have the plus or minus, just the sine or cosine. And then we have our roses. If you look at that page with all the different graphs there, we have our roses here. The roses have different numbers of petals depending on what your value for n is. If your n value is even, you will have twice that many petals. Whatever n is, you're going to have twice as many. So when n is 2, you get 4 petals. If n is 4, you have 8 petals. If n is 8, you have 16 petals. If your n value is odd, you just have that many petals. So if n is 3, you have 3 petals. If n is 5, you have 5 petals. If n is 7, you have 7 petals in your roses. All right, so for our roses, we're going to write down a couple things here. If n is odd, there are n petals. And we have a period of 2 pi. So if n is odd, we will have n petals, and our rows will have a period of 2 pi. If n is even, there are 2n petals, and the period is just pi. So if n is odd, we have less petals, but we have to use every angle around the unit circle to see them all. If n is even, we only have to go halfway around the unit circle, but we end up with twice as many petals. So talk to me about how you would know just from looking at an equation. We talked about things that we look for to be able to tell circles and Limousines apart. How would you be able to tell a circle apart from a rose? There's an n value. Roses have n next to theta. All right, 2 more that we're going to look at. Lemniscetes. If you look at that page with all the different graphs, what do the lemniscetes look like?
Figure 8 bow tie.
Looks like a bow tie, or like an infinity symbol. Lemniscetes are bow ties or infinity symbols. How are we going to be able to tell from just the equation whether it would look like a bow tie or whether it would look like a tipped bow tie?
What? Huh?
Looking over here. How can I tell from the equation whether it's going to look like a bow tie that's on straight or whether it's tipped?
The sine or cosine?
Sine or cosine. Which one makes it tipped?
Sine.
Sine. You're going to end up with a crooked bow tie if it's a sine. If it's cosine, it's going to be on straight. Lemniscetes have a period of pi. How could you tell these equations apart from the others? What could you look for in the equation so that you would know that it's a lemniscete instead of another shape?
2 theta.
2 theta. It is always going to have 2 theta, but my roses could have 2 theta. So how do you tell these apart from a rose?
Squared.
Squared. Your R value is squared. And then our very last one is called the Spiral of Archimedes. All the others will come back and join where they began. Our circles, wherever we begin, we're going to come back and join that. When we talk about our Limousines, it's going to come back. The last point that we plot will be right on top of the first. Same thing is true for my roses. And even for the lemniscetes. Do the spirals join back up with their starting point? No. These have no period. They're going to spiral outward, and you're never going to have a repeated R value. How can you tell these ones apart from the other types of graphs? It has a B.
Oh, no, thing is a
No what?
no one of the things.
What do you mean by one of the things?
You know what I mean by the things.
Yeah, I just want you to say it though.
Okay.
No what?
What?
No sine or cosine, yes. So if you're looking at a polar equation, r equals something, and there's no sine or cosine in it, it's going to make a spiral. We've got a plus or a minus, usually, no sine or cosine. All right. I want you guys to look down at the bottom portion of the page, and there are 9 different equations there. I want you to practice identifying what type of graph it is. So I want you to look at those 9 equations at the bottom. What types of graphs are they? You doing okay, Carrington? Okay. What types of graphs are they? What kind of graph is number 1? Yep, lemniscate. All right, so number 1 is a lemniscate. What is number 2? Yes. This is a spiral of, we pronounce it Archimedes. Spiral of Archimedes. What about number 3? This is a rose. How many petals does this rose have? 3 petals. What is number 4? Limousines. This is a limousin. What about number 5? We've got another spiral here. What about number 6? That is a circle. Seven. There's another rose. How many petals? 3 petals. What about number 8? There's another circle. Would this circle be left, right, above, or below the origin?
Above.
Above. What about the other circle, number 6? Sorry, number 6. Would that circle be left, right, above, or below?
Oh, wait. Yeah, right.
To the right. Because remember, cosine goes right and left. So if it's positive, we'll be right, and if it's negative, we'll be left. Sine is the one that goes up and down. So this is to the right of the origin. All right, and I think I threw some people off by asking that. Number 9 is what? That's another limousin, yes. All right. So now that we've practiced identifying these, I want to practice doing some graphs. We need to know what kind of graph we're going to be making so that I know what the period is, so I know how far out to make my table. So if you flip over to the back side, number 1, r equals -2 cosine theta. What kind of shape? This is a circle. What's the period on our circles? Period is pi on our circles. So on my table, I need to go from 0 to pi. The only way you're going to fit from 0 to pi on the table is if you take each one of these cells and you cut them in half. So on the table, you need to take each set of boxes and cut them in half. Otherwise, you will not be able to fit all the way to pi on here. All right. So let's do this in radians around our unit circle. I'm starting at 0. What comes after 0 radians? Pi over 6. And then what? Pi over 4. Pi over 3. Pi over 2. What's the next one? 2 pi over 3. 3 pi over 4. 5 pi over 6. And pi. That's as far as we need to go for our circles. You following?
I get what you're doing now.
Okay, good. We're just writing down what we're using as our input. All right, so now one at a time, I'm going to take these theta values and we're going to substitute it in. So I have -2 cosine 0. What's cosine of 0? It's 1. So I have -2 times 1, right? -2 times 1? -2. Okay, so for those of you guys that were not here on Friday, we can have negative r values. R stands for the radius, and most of the time when we think about this, like radius can't have negative values. But when I'm graphing in polars, let's see, here's 0 radians right here. If I have a positive r value, then I'm going to count to the right. And if I have a negative r value, I'm going to go backwards along that same line. So how far to the left would I want to go? 2 units to the left. So I'm going to have a point right here. And I'm going to do my best to color code my points so you guys can see which ordered pair is going with which point and how we're ending up with this shape. All right. So now I get to this. I've got -2 cosine of pi over 6. What is cosine of pi over 6? √3 over 2. So I end up with -√3. I don't really know where to plot that on my graph, though. Can you guys grab your calculators and tell me what -√3 is in its decimal form? Yep, negative 1.732 when we round it. I'm just going to write down negative 1.7 because I just need to ballpark on my graph about where this is. Right. Yep. Did you make sure that you're in radians? That's okay. We were working in degrees up until today again, so make sure that you're in radians. Did that fix it? Okay. While you guys are checking on that, here's pi over 6. Where would I go for negative 1.7? Yeah, I'm going to have to head this way, and I'm not going to be quite as far as 2. So right about here. Were you guys able to get the correct value now? Yeah. Awesome. All right. I'm going to substitute in pi over 4 now. So negative 2 cosine pi over 4. What's cosine of pi over 4? Yes. Cosine of pi over 4 is radical 2 over 2, so we're going to end up with negative radical 2, which you're absolutely correct, is negative 1.4, about. So I've got negative 1.4. Here's pi over 4, so I need to go backwards right here. It's going to be almost at the halfway point between those two circles. Right. Negative 2 cosine of pi over 3. What is cosine of pi over 3? 1/2. So this gives me what as an output? Negative 1. So right here. What's cosine of pi over 2? 0. So the output here is just 0. I'm going to land right on the origin.
So is R? Is that the X value?
R is, for the way these functions have been written, theta is our input and R is our output, but R extends in all directions. It kind of radiates out from the center. Do you see those circles around this graph? That's what we're using to count our R. If it's a positive R value, we follow that angle measurement however far out R is. If R is negative, then we just move backwards along that same angle measurement. What would I get for output when I use 2 pi over 3 in the place of theta? 1. We get a positive 1. 2 pi over 3 is right here, and since it's a positive R value, that means I just follow along that line, so right here. What about 3 pi over 4? Square root of 2, which is about 1.4. So 1, right about the halfway mark. Are you guys starting to see this circle shape show up?
I guess.
5 pi over 6. Square root of 3. Because it's negative root 3 over 2 times negative 2. So we end up with a positive root 3, which is about 1.7. So that's going to go right here. What's cosine of pi? What's just cosine of pi? Negative 1. So I have negative 2 times negative 1, so my output would be 2, which lands me right on top of that first point that I plotted. Because remember, my first point was 0 radians, but negative 2. When I get around to pi, positive 2, same spot. So here's my circle. How are we doing? Clear as mud?
Absolutely.
Fantastic. Huh? You guys okay if we start moving on to number 2? I don't know if we'll get all the way through it, but I at least want to figure out what kind of graph is it, what is our period, and we'll start finding some values. What kind of graph are we going to be making here? A Limousine, yes. What's the period for all of our Limousines?
2.
Yes, period of 2 pi. So we're going to have to take all of these little cells in this table here, we're going to have to cut them all in half. We're going to have to add 3 on the end so that we can go all the way out to 2 pi. So I need to go around the unit circle. I'm going to recopy those theta values that we had before. So 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. What comes after pi as I'm counting around my unit circle? 7 pi over 6.
4 pi over 3.
Not yet.
Or, wait, sorry, the 5 pi over 3.
5 pi over 4. And then 4 pi over 3. What next? 3 pi over 2. What comes after 3 pi over 2? 5 pi over 3. 7 pi over 4. 11 pi over 6. And finally, 2 pi. You are welcome to grab your calculators as we're looking for output here. Make sure it's in radian mode, though. I have 1 minus 2 sine theta. What's sine theta? Yeah. We're putting in 0 in the place of theta. Sine of 0 is 0, so I have 1 minus 2 times 0, or 1 minus 0, so I have an output of 1 here. So I have a point right here, 0 radians, my radius is 1. Let's do pi over 6 next. 1 minus 2 sine pi over 6. What's sine of pi over 6?
0.
My whole output will be 0. Does anybody remember what pi over 6 is? Sine of pi over 6? 1/2. So I have 1 minus 2 times 1/2, or 1 minus 1, which gives me an output of 0. So it's going to be right here. What about when I use pi over 4 as my input? What did you say? So I have 1 minus square root of 2. What would that be in its decimal form? About 0.4, yes. Actually, it's negative 0.4, I believe, because we're subtracting. Negative 0.4. So here's pi over 4, and I need to go negative 0.4, so it's going to be back here. What about pi over 3? One minus radical 3. What is that in decimal form? Negative 0.7. So here's pi over 3. I need to go backwards almost to the 1. What about when I use pi over 2 as my input? So I have 1 minus 2 sine of pi over 2. What's sine of pi over 2? 1. So I end up with 1 minus 2, which is negative 1. So here's pi over 2. I need to go backwards 1, so it's right here. I'm going to trace in what we've got so far. So from that first point, the one that's light blue, it's going to loop up just a little bit, and then it's going to go down through those points. If we had some pi over 12s, we would be able to see why it's going up above the x-axis there, and then it comes down through the origin. So this is going to be one of those Limousines that has that inner loop. What about when we use 2 pi over 3 as our input? Pop it into your calculators if you need to. When we use pi over 3 as our input, or sorry, 2 pi over 3. I'd like to get 3 more points before we call it a day, and we've got just a couple minutes left. Where's our next point going to be? Yep, negative 0.7, because we end up with 1 minus radical 3 again. So 2 pi over 3, that's going to be right here. What about 3 pi over 4? Negative 0.4, because I end up with 1 minus radical 2. What about 5 pi over 6? 0. And the last one that I want to get here is pi. What do you get for pi?
-1.
Close.
+1.
+1.
I'm so surprised.
All right, we're going to finish this graph out tomorrow, and we'll do several other graphs as well. You guys are going to be doing a project where you have to pick out 4 of these graphs and you're going to do them on a single polar plane. So start looking at these different graphs. Which ones pique your attention? You get to pick out the 4 that you want to use, okay? Which ones do you find the most interesting? Which ones do you find the most visually appealing? I'll show you some examples of the project that you're going to do for me tomorrow and Wednesday so you have some idea as you start thinking through what you want to do.